Hello and welcome to a new Ostrich video, and today I want to start a little series about radio navigation, and this is the first part of it. And for radio navigation we usually need a ground station and the necessary equipment in our aircraft. So in the main time that means we have a viewer station on the ground and the viewer indicator on our aircraft, or an NDB station on the ground and the ADF, the automatic direction finder, in our aircraft. And as the NDB is the most basic radio station we can have on the ground, I will start with the NDB navigation. So NDB stands for non-directional beacon, and it says, or what it does, it can say I'm here and nothing else. Just can't give you any direction. So an NDB can say I'm here, and the ADF in your aircraft can say the NDB is over there. It can point at the NDB, and that's basically it. So that's not much, but this is all we need for basic navigation, because we know there's an NDB and we can fly towards it. We have a known point on the map and we can navigate from this. So if you are looking on a map like this one of the area around Hamburg, you will find an NDB marked with the symbol, a circle with circles of dots around it. And at least in Germany, maybe in different regions it's a bit different, you will always find an NDB close to an airport and aligned with the runway, so that you can use an NDB for approach as well. And this brings me to the first point. We basically have two different types of NDBs. So we have en route NDBs. These are the ones that have 3-letter markings, like the Nordholz NDB here with NDO, and the Hamburg NDB here with HOS. And these NDBs have a range from 50 to about 100 nautical miles, so that's quite nice. Quite long range, and you can use them for en route navigations, but they are always aligned with the runway of the airport, so you can use them for approach as well. So the Nordholz NDB you can use for en route navigation and then use for the approach into Nordholz Speaker. And then we have so-called localizer NDBs, and these are the ones used for approach as your localizer and so on and so forth. They have a range from 15 to 24 nautical miles, and they are marked with a 2-letter code. So like the Fürstenwalde, Fuhlsbüttel NDB right in front of runway 5 of Hamburg Airport, and the GT NDB are here as well, again aligned with the runway. And these NDBs are used for approach as localizer, giving you your outer marker and so forth. Now, an NDB uses a frequency spectrum from 200 kilohertz to 526.5 kilohertz. And this is a range in Germany and Europe. In North America, you have slightly different ranges because radio is broadcasted there slightly different, and you have to keep the radio frequencies what can be in the same reach apart from the navigation frequency. And this is the reason why United States is a little bit different than Europe. But if you look at the unit, you see it's kilohertz, and this is a full magnitude lower than the megahertz frequencies we use for talking with ATC, ILS approaches, and our VORs. And this relatively low frequency bands brings us some advantages, but also some disadvantages. And these advantages and disadvantages are lying in the way these waves with these frequencies are traveling through the air. So if we think this here is our Earth, this is a atmosphere, and on top or still a part of the atmosphere is the ionosphere. And here we have our NDB antenna. So this antenna basically sends out two different types of waves of this frequency. So first we have the ground wave. that travels parallel to the ground until it gets absorbed by it completely, or so strong that we can't receive a good signal anymore. So this is the first type of wave. And the second type of wave is the so-called sky wave. And the sky wave goes up and gets reflected by the ionosphere, then bounces back to Earth and gets reflected again to the ionosphere and back and forward. And because of this reflection, it can travel over a really large distances. So if you are at night with perfect atmospheric conditions, the signal can travel easily over 10,000 nautical miles, so no problem whatsoever to transmit over oceans. And this is also the reason why when you're flying across the Atlantic, you change your VFH radio to your HF radio, because then you're using this effect to transmit the voices. But this is an advantage because it gives you a lot of range, but it can also cause a lot of problems. So first of all, it can happen that, as you see here, the ground wave gets absorbed before the sky wave hits the ground anymore. So if you are in this zone, you won't get a signal at all. So this is a dead zone where you don't get a signal. It's usually not as a big problem because sky waves doesn't hit only in this angle, it also hits in this angle, and then it gets reflected in a different angle. But if you have geographic features blocking some of this waves out or whatsoever, you can gather some dead zones where you can't receive your signal. This is one part. The other part is the interference between the sky wave and the ground wave. So if we look at our radio wave, it looks somewhat like this, so sine curve. So you see the wave goes up to +1 and then it goes down to -1 again, and so on and so forth. So let's assume this is our ground wave and it's traveling this way, so no problem at all, we can easily receive this. But if now the sky wave overlays with this wave, and if you're lucky, it overlays this way, so they match up perfectly. In this case, the signal gets amplified and we can easily receive it. But it's not so likely that they perfectly match each other. So if you are, for example, have the situation that they are a little bit off, you will see still that gets added and you still have somewhat of a signal. But if they are aligned like this one, so that they are half bandwidth apart from each other, they align like this wave, and you have the +1 value of the sky wave plus the -1 value of the ground wave, and +1 plus -1 equals 0. So these waves would completely cancel each other out and we have no signal whatsoever. And in real time we are somewhere in between. So depending on the area where we are, we can have problems receiving the signal from our NDB station. And this happens especially at dusk and at dawn, because in this times the ionosphere is changing its structure and therefore the way sky wave gets reflected. And because it's the end of the night or the beginning of the night, this effect is called night effect. And keep in mind, at this times of the day, your ADF reading is the most unreliable. Well, this is the first problem of these waves. The second problem is that they can get bent. So if we are in the coast area, so we have the NDB here, our coastline here, and the water here. So now the ground absorbs the radio waves differently than the water. And because of this, the waves hit the coast on a shallow angle, they get reflected, they got bent. And therefore they are no longer traveling in a straight line from the NDB to our aircraft. So what this means if we are flying this way, so we have, if we are here and we are on a rectangular angle of the signal towards the coast, everything is fine, there's no bending going on, and we get a reliable signal. The same is true if we are within plus 30 degree minus 30-degree range of this rectangular angle to the coast. But if we are over here and we're receiving a signal that hits the coast on a shallow angle, the signal gets bent. And you easily see now that the radio line is not longer traveling in a straight line. So if we are here with the aircraft, we would receive the signal that the NDB is somewhere over here. So when you're flying parallel to the coast, you have to keep this effect in mind. A second nasty effect that can happen and is the mountain effect. So the mountain effect is happening because the radio waves can also be reflected. For example, reflected by a mountain range. So we see we have the NDB over here, and this aircraft gets the indication from the ADF. NDB is over there, and this is correct. But in this aircraft, we have the nasty side effect that the NDB sends out the signal in all directions equally, but from this direction it gets reflected by a mountain range. And so this aircraft receives, the ADF receives the signal that the NDB is over here because of this effect, and this you can easily see is a really dangerous situation because you are not flying towards the NDB, you are flying towards a mountain range. And how to protect yourself from such possibly deadly mistakes is, first of all, keep this effect in mind, fly higher than the mountains, and if you have mountains along with your NDB, double check your position to avoid these effects. And lastly, ADF is also sensible to the atmospheric conditions in our troposphere. So if you, for example, have a thunderstorm with lots of lightning, so a lot of charge in the air, the ADF needle will possibly go towards the lightning strikes and not anymore to the NDB, so you can have really erratic movements of your ADF needle and basically run out impossible to use for navigation. And then also you have to keep in mind that when the ADF is calibrated with the ADF antenna on the bottom of your aircraft, it's calibrated for a level flight. So if you are banking the aircraft, the signals from the radio NDB station will hit your aircraft in a different angle because you are banked, and therefore you will get a mistake as well, and reliable readout from your ADF you get only in level flight. So that's all the theory about the NDBs. In the next part we will go flying and use this knowledge to find our way around this area. So all that's left to say now is thanks for watching and see you at the next time. And yes, if you have questions, comments, just write them in the comments below and I try to answer them as quickly and correctly as possible. And then see you at the next time. Bye bye.